Okay, here we go once again. Chemistry 3202, course overview, review. In this section we're going to do Unit 2, Section 3, Lesson 5, Polyprotic and Polybasic species, and we're also going to do the Polyprotic and Polybasic titration curves as well. Okay, so here we go. This is dealt with on page 609 of your textbook, so you might want to go have a look. And there's a few items there that are related to this material as well. Don't forget, answers are in the back of your book, and they're also at the end of the chapters. And if you have any of these that you want to have looked at, don't forget to take advantage of our online tutor and or drop a line to the discussion postings there so we can have a look and see what you want us to answer. Okay, here we go. Here are the outcomes for this section. Okay, now we're going to start our little discussion here on polyprotic and polybasic species by looking at a monoprotic acid. Now, monoprotic simply means mono means one, protic means a hydrogen ion. So we're going to be talking about acids that have only one hydrogen that they're capable of donating. And a couple of examples of some of these acids would be things like hydrochloric acid, nitric acid. So with hydrochloric acid, we're looking at this idea that the hydrogen there is going to be donated to the water. And that would be a Bronsted-Lowry transfer, right? So that hydrogen is being transferred to the water. That's the Bronsted-Lowry definition, where the hydrochloric acid is acting as the acid, it's donating, and the water would be acting as the base. It would be accepting the hydrogen. Okay, if we look at another one, say nitric acid, same sort of principle here. The nitric acid is a strong acid. You can check your acid-base tables. And it too is going to donate its hydrogen. And because, of course, these guys are strong acids, this is going to be 100% forward. All right, so no double arrow. Now that doesn't mean to say, oh, all monoprotic acids are single arrow. You could have something like acetic acid vinegar that's monoprotic as well. Now, when we look at this, there we go. So there's vinegar, and in the case of vinegar, we know that vinegar is a weak acid. So this guy's going to donate. Remember, that hydrogen there is the acidic one because that's on the carboxylic acid. And in this case, of course, this is going to be the weak acid, so we're going to need a double arrow here. There we go. Okay. So what we want to look at is say, well, these guys are very similar in characteristics. They're only donating, or they're only capable of donating one hydrogen. Even though there's more hydrogen here on this in this acetic acid, only this one is donatable. This is the only acidic hydrogen in this compound. The other three are held too tightly to be acidic. They're not going to be released. So what we need to do is we're going to say, well, what's this going to look like from a titration curve perspective? And what we can come up with here is we say, well, there's only going to be one hydrogen donated. So therefore, there's only going to be one equivalence point. So when we start titrating these, so I'm going to take a strong acid. When we start titrating this, hydrochloric acid, of course, it stays relatively level and it stays really, really low because hydrochloric acid is a strong acid. So what's happening here now, the sodium hydroxide that we might be adding to this is starting to neutralize it. And then all of a sudden, we know that the pH is going to shoot up to give us a vertical region. And then once all that hydrochloric acid is neutralized, it begins to level off because we have excess base. So we got excess sodium hydroxide here, which causes the pH to be up around, say, 12-ish, depending on the concentration. Now, when we look at the vertical region, of course, the equivalence point is the midpoint of the vertical region. We did that in the last lesson. So this is the point where that hydrogen right there is completely transferred. So right here, of course, the hydrochloric acid is withstanding the sodium hydroxide. It's neutralizing all the sodium hydroxide. So every step along the way here, we've got excess hydrochloric acid until all of a sudden, all the hydrochloric acid now has been neutralized, and this is why the pH would shoot up. Because now there's no more HCl in the container. It's all been neutralized. Any more drops of sodium hydroxide, of course, now we've got excess base. So that would be the point where the titration curve would be indicating that that hydrogen has been completely transferred. So remember, the axis here is going to be pH, and this guy is going to be the volume of titrant. And for us, let's assume that it's going to be sodium hydroxide, a strong base. There we go. So that's a single vertical region, and this would be true for nitric acid. I could easily use this and say instead of hydrochloric acid, that would be nitric acid. The curve would look very similar. With acetic acid, remember, acetic acid is a weak acid, so what you're going to see is you're going to see a curve that's going to be more up along like that, and then it's going to level off, right? Because acetic acid now is a weak acid, so it's going to have a much sharper incline because it's less able to ionize, and therefore the vertical region is going to be up further, remember? So the equivalence point pH is going to be up here. But the characteristic thing here of this curve is that each of these is a monoprotic acid. So no matter whether we start low or high, or whether the curve is very level or whether it's slanted, the important thing here is both of these would have one vertical region. So both of these would be representing a single proton transfer. Okay, what we're going to talk about now are polyprotic acids or bases. In this case, polyprotic acids. In this case, these are acids that are capable of donating more than one atom of more than one proton at a time, more than one hydrogen. So some examples here would be, for instance, sulfuric acid. In the very first sulfuric acid, we have H2SO4. Now remember what Bronsted-Lowry said? The Bronsted-Lowry definition of an acid said that it occurs in a single proton transfer, one hydrogen at a time. And here's the reason for what they're saying. This sulfuric acid has two hydrogens that can be donated here. But what happens is, as the first one is donated, so the sulfuric acid is acting as the acid, water is acting as the base. What's happening here, this process of transferring one single hydrogen, we end up getting a conjugate base here, hydrogen sulfate. Now what's happening is, even though this is recognized as a conjugate base in this particular reaction, because it's grouped with the sulfur here, the sulfate, what's happening is we can continue to add our sodium hydroxide here, and in another step, even though this is a conjugate base in this reaction, in the next step of this reaction, HSO4 is going to act as a weak acid. So what's going to happen as we continue to add sodium hydroxide in our titration, that next hydrogen is going to come off, but that HSO4 minus is now a weak acid, which means we're getting the hydrogen removed at two distinct pHs. This first guy is going to come off real early because this is a strong acid. This one here is going to come off much later because it's a weaker acid. And what we end up seeing is two distinct steps for the removal of these two hydrogens. Okay? So in this case over here, this is acting as the conjugate base as well. So there we go. All right, so what's this going to look like in terms of a titration curve? Hold on now, let me just block this out. All right, when we look at this guy, we want to be able to write the overall reaction, and in a sense, this one here is going to be crossed out because it's being produced in this step, and then it's being consumed in step 2. So for a complete neutralization, if we add sodium hydroxide so we completely neutralize the sulfuric acid, it's going to happen in a two-step reaction. So just like your reaction mechanism, it's a two-step reaction. And overall, this guy is acting as an intermediate in the process of getting from H2SO4 to SO42 minus. So we notice here that there's two H3O pluses, so this is doing two hydrogens coming off, and we can show the overall reaction. Now, just like mechanisms, we know that this overall reaction does not happen in one step. We know that this is a two-step transfer, and that's the important point. All right? And again, the intermediate here is now a weak base, so that's what's going to influence the pH where each of these steps occurs. Okay, so if we do a titration curve for this, this is going to be a diprotic titration curve because there's two hydrogens being removed. We're still going to start really low, aren't we? Because sulfuric acid, the very first step, is a strong acid being neutralized. So we're still going to start low, and we're going to start going across. And all of a sudden, when every last bit of sulfuric acid has been neutralized, we see a vertical region here. And again, the midpoint of the vertical region is where the pH of that equivalence point. Now, you might say, well, why didn't it shoot all the way up to pH 12, the pH of sodium hydroxide? Well, the reason it can't shoot up yet is because when this step happens right here, we're producing this weak acid. And this weak acid now is going to be in excess, and it's going to have a pH much lower than pH 7. So what we're going to see happening here is as we continue to add a little bit more sodium hydroxide, as we continue to add the sodium hydroxide, we see that the pH would shoot up. But what's happened now is all the sodium hydroxide has neutralized the sulfuric acid, but now the HSO4 is in excess, and that's going to keep the pH below 7. We continue to add sodium hydroxide, and the sodium hydroxide is being neutralized by that weak acid, HSO4. And eventually what happens as we begin to continue to add sodium hydroxide, once again the pH would shoot up once more. And what we're seeing here then is that this is now the midpoint of the next vertical region, which is going to be the pH where this guy is completely neutralized. And then the pH would skyrocket to pH 12 or so, because that's where we would have the excess sodium hydroxide, right here. Okay, now there's a couple important things here. We notice that it does not happen as one step. We don't see both of these hydrogens coming off at the same pH. These hydrogens come off at 2 different pHs. And this is a distinctive graph for a diprotic acid. So the hydrogens are coming off at 2 different pHs because the first guy's a strong acid, this guy's a weak acid. And there we go. Okay? An important point to note here, 2 vertical regions, 2 equivalence points. That's representing each individual hydrogen that's being removed. Another thing they like you to show on these titration curves is what species is in excess at each level. So in the first plateau, H2SO4 is in excess, and that's why the pH is down around 2-ish. As the first hydrogen's removed right here, you state that, the first equivalence point. This is the first hydrogen that's donated. And then the reason that this next plateau is below 7 is because this HSO4 ion is what's in excess. That's what keeps the pH below 7. We continue to neutralize here, then all of a sudden the pH shoots up again. That hydrogen now has been completely removed. And then what happens, of course, the pH would shoot up to the pH of the sodium hydroxide. Now you notice what I'm doing here? I'm indicating which species in this reaction that's in excess. And it's this guy here, SO42 minus now is in excess. So you can see each hydrogen that's been removed. Okay? And I might also want to indicate here that the NaOH now is in excess. So we got excess OH minus. And that's what keeps the pH up around 12-ish. All right, so there we go. So that's a diprotic acid. Here we've got another situation where we got something that's called polybasic. In this case, we're going to be going in the other direction. So we can take something like the carbonate ion. Now the carbonate ion we say is a base, and it's a fairly strong base. If you look on your acid-base table, it's well down there on the right-hand side. So it's a fairly strong base here, and we can say that because this is 2 minus, this guy has the potential to attract 2 hydrogens. So from the Bronsted-Lowry perspective, this guy is going to attract that way. Okay? And what we're seeing then is the CO32 minus is acting as a base, and the product here, HSO4, is acting as, even though in this case, in this first reaction, it's acting as a conjugate acid, when we take it down to the next level and start adding more hydrochloric acid, in this case, the HCO3 minus is now going to act as a base, a weak base. And there we go. So once again, if we write this as an overall reaction here, the HCO3 is really acting as an intermediary. But the important thing here is even though it's an intermediate, it's influencing the pH of step 2. Because HCO3 minus is a weak base, it's going to keep the pH up a little bit. There we go. Okay. So the question would be, well, what does the overall reaction look like? Well, we've crossed out our intermediates, and we're saying here that CO3 2- is capable of neutralizing 2 moles of hydrochloric acid, and it's going to produce H2CO3 and 2Cl-. Our titration curve of this, well, we're adding hydrochloric acid as our titrant. So in the beginning, we're going to start off real high, because that's going to be the pH of CO3 2- when it's in excess. It keeps the pH relatively high, up around 10, 11-ish, depending on its concentration. When all the CO3 2- has been neutralized by the hydrochloric acid, what we see is the pH would plummet. We see our equivalence point, the midpoint of the vertical region. That's when the first hydrogen has been added. Now what happens here is the pH is kept high because this guy has basic properties. HCO3 is going to be above 7, and what we're going to see is the curve is going to level off above 7. And what we're going to continue doing here now is keep adding hydrochloric acid. So now we're going to have to neutralize this base. So it stays a little bit level, and then all of a sudden when we've added enough hydrochloric acid to neutralize that, the pH is going to plummet, and it's going to drop way, way down to the pH of the hydrochloric acid because the hydrogen's in excess here now. Okay, so in this particular reaction then, once again, we see 2 vertical regions. The first one is indicating the addition of the first hydrogen that's accepted, and this one's representing the second step, or the second hydrogen that's accepted. The species that are in excess, in the first case, it's CO3 2- that's in excess. That's what keeps the pH high. Then we add a hydrogen, and then the second plateau is going to be above 7 because this guy now is acting as a weak base, and it's in excess. Then we add the second hydrogen, and then H2CO3 is present in a large amount because it's in excess along with the hydrochloric acid. Okay, so we also now have some excess H3O+ from the hydrochloric acid. There we go. Now one little thing I forgot to note up here, if we, the source of carbonate ions, of course, carbonate ions cannot exist by themselves. If you're going to try and get some material that contains carbonate ions, what you're going to have to look for is something like sodium carbonate. And of course, that's an ionic compound now, so this is going to be our source of carbonate ions. All right, so I forgot to tell you that, but there it is. Okay, so lots of times you might have something like magnesium sulfate or sodium borate or something like that, sodium phosphate. Remember, sodium is always a spectator. Its sole purpose in this case is to get the carbonate into the solution. There we go. So that's a polybasic, and you notice it's slightly different. It's very similar to what we did in the last graph, but in this case it starts high because the base is what's in excess. And as we continue to drop, because the hydrochloric acid is being added more and more and more. All right, so again, 2 vertical regions, diprotic acid. Okay, here's an example now is the titration of sodium hydroxide with phosphoric acid with some sodium hydroxide. Now, phosphoric acid is H3PO4. And this guy, of course, has 3 donatable hydrogens. So what's going to happen here is it's going to go in a series of steps. The first one comes off to produce H2PO4. Now, if you're not sure what you're going to get on the other side, simply look at the acid-base table, and for H3PO4, this is going to be listed as the acid, and right across from it, you're going to see this listed as its conjugate base. So you will see that on your acid-base table. As we continue to add some more sodium hydroxide, the second hydrogen gets transferred. So the second hydrogen gets transferred. And again, if you're not sure what you're going to get on the other side, locate this one on your acid-base table as an acid. This one will be located right next to it as a conjugate base. And then what happens if we continue to add sodium hydroxide? We're going to see that the last hydrogen now is going to be donated. So this is going in a series of 3 distinct steps. 3 distinct steps. And if you locate each of these guys, they're all weak acids. But as we go down the table, we'll find that this guy is a weak acid, this one's weaker, this one's weaker still. So each of these acids is getting weaker and weaker and weaker as we continue to go. And what we're going to see then, you guessed it, it's going to be an overall reaction which shows us the 3 steps because it's neutralizing 3 moles of sodium hydroxide. But the important thing is it doesn't occur in one step. It occurs at 3 distinct steps with 3 distinct pHs. So what's this going to look like? Well, it should look like a curve that, let me just uncover it as we go. It's going to start real low, and then the pH is going to shoot up 1. All right? Now again, the pH doesn't go all the way up to pH 12 of sodium hydroxide. It stays low because H2PO4 now has acidic properties. So we're going to see that. And then what we're going to do is continue to add the sodium hydroxide, and then it's going to level off again. There we go. And we'll see the second one coming off. And then as we continue to add sodium hydroxide, then we'll see the third leveling region. So there we go. So in this case, because we had 3 distinct removals, we're going to see 3 distinct equivalent points. There we go. Now, on a test or something, really determining where these pHs would be located, it's going to be tough for us to do, so we just generally sketch the curve. Don't put any pHs in here unless you know the pH of your acid and the pH of your sodium hydroxide. You could put your beginning and your end ones in here. But the ones in between are going to be a little bit complicated there to find out. But in any case, what we want to show is the fact that you recognize that it's 3 vertical regions, 3 distinct removals. There we go. Okay. So this guy would be a polyprotic acid. In this case, here's a typical problem, and it's simply saying write each reaction as a series of net reactions showing what's going on. So in this case, phosphoric acid with sodium hydroxide, and it says only 2 steps. Okay, only 2 steps. So what we're saying then is this is probably going to be the first one and the second one. So phosphoric acid, H3PO4, we got 1 transfer, H2PO4 is produced, and then the second guy is going to be transferred. There we go. Sodium sulfide with hydrochloric acid. Well, remember, sodium is a spectator. Its only purpose is to bring the sulfide into the reaction chamber. And there we go. So it's going to be Na2S. And HCl is a strong acid. So what we're going to see is the S2 minus here is a base. It's going to accept the first hydrogen. Okay. And then HS minus is going to continue in the second step to accept another hydrogen from the H3O plus. And then we get H2S. Now remember now, hydrochloric acid is a strong acid, so it really exists as H3O+. Here's another one, selenic acid. This guy looks like it has 2 hydrogens that it can donate. And we're going to react it with some sodium hydroxide or just hydroxide, because the sodium is going to be spectator. And what we're going to see again is 2 distinct steps here. The first hydrogen comes off to produce HSeO4 minus. And then the second one will come off at a higher pH. HSeO4 1 minus becomes SeO4 2 minus. There we go. So 2 distinct steps. Here's another one, citric acid. This guy is a compound that has 3 carboxylic acids in it, and they've written it this way to show you the 3 hydrogens from the carboxylic acids. And in this case, they want you to do 2 steps only. So we're going to take off only 2 of these hydrogens here. And we're going to take the first one off in the first step. And you notice here what I've done? Rather than writing out H3C6H5O7, I simply said, hey, we know that this guy is going to be a triprotic acid, so I'm going to write this H3A and indicate that the important thing here is to show the transfer of the hydrogens to produce H2A minus. And then that next one's going to come off, so it's going to be H2A minus producing HA2 minus. There we go. Now if you want to write it all out, you can. If you want to write out the entire chemical formula here, you can. Feel free. Okay, here's a typical question from a public exam. It says, sketch a titration curve for the titration of 0.1 molar phthalic acid. They give you the formula. So it looks like there's the 2 acidic hydrogens. It says with sodium hydroxide, and assume 2 quantitative steps. All right. So what we're saying then is that this guy is definitely a weak acid. There's only 5 or 6 strong acids from our table. So what we're going to see then is we're going to do our reaction and say, all right, this guy's going to donate the first hydrogen here. So we're going to take off a hydrogen. That's going to be HC8H4O4 minus. And then we're going to take off the second hydrogen. There we go. And our titration curve of this is going to be a weak acid, so it's going to start a little bit higher than 2, say. And here we go. So it's going to start a little higher than 2. It's going to level off, and then it's going to shoot up. And we're going to assume then that because this guy has a donatable hydrogen, it's going to be a weak acid now. Up here it's a conjugate base because it's linked with this acid. But down here it's going to act as a a weak acid because now it's being reacted with the OH minus. And what we're going to see then is another equivalence point like that. So first step, second step. And that's what they're looking for. They would really want you to write pH here, and they would really want you to write down what the titrant is. In this case, it's sodium hydroxide. They want you to show each species, and that's the species from, right? Because essentially what we're looking at is this is step 1 right here. Okay? This is step 2 right there. Okay? So that's basically how you would write that in there. Let me just clean this up. There we go. One more for the road. Here's another one that says sodium hydrogen phosphate is titrated with hydrochloric acid. It says only one quantitative reaction is observed. Write the Bronsted-Lowry equation. Okay, so sodium hydrogen phosphate, what we're looking at here is that you may have to check out your table of complex ions here to figure out what hydrogen phosphate is. But in any case, hydrogen phosphate is HPO4 2-, so it's going to require 2 sodiums in order to neutralize it. So in a sense, what we have here is we're really not looking at the sodium is not important. It's the hydrogen phosphate that you guys would want to look up. All right, and that's HPO4 2-. Don't confuse it with H2PO4-. That's dihydrogen phosphate. All right, so check the names on your table. Okay, so what we're looking at, we're saying only one quantitative reaction is observed. So we're taking this guy and we're going to donate one single hydrogen here. So that's going to be the donation like that. So this guy is really, even though it's got a hydrogen here, because it's mixed with a much stronger acid, this guy is being forced to act as a base. It's amphoteric. And remember, amphoteric substances, their role depends on what they're mixed with. If they're mixed with a stronger acid, then they're going to act as the base. If they're mixed with a stronger base, then they're going to be forced to act as an acid. So in this case, the HPO4 2- can act as an acid or a base, but because it's mixed with a much, much stronger acid, it's going to be forced to act as the base. So this question, that's what they're trying to look at here. Okay, now I'm taking this even further. I'm going to do the 2 titration here. So this guy's going to continue on then to take another one. And therefore the titration curve of this, it's a weak base. So that means the HPO4- is going to start high, but much lower than 10, because HPO4 2- is a weak base. And it's going to drop, drop, drop until eventually it drops off to produce the first point. And then H2PO4- is going to be present, and that now is going to be a much lower pH. And of course we see the second gain down here. Now, the importance of this is the fact that now we have 2 different pHs. We have to decide, they could further ask you in this question, what indicator would you use? If I gave you this on a curve and say, which indicator would you use to show me the first equivalence point? What you'd have to do is you'd have to look for the first equivalence point and say you want something that changes within this pH range. And I'd have to look up my indicator table now, and if I was looking for the first equivalence point, it would have to be an indicator that changes color here. If I was looking for the second equivalence point, that's how they would say it, I would have to look for something that changes in this range right here. So I would use two distinctly different indicators to indicate which one I was looking at. All right? If I use the wrong indicator, then I may not see the right equivalence point. And you notice here that there's two different volumes. As I drop down my curve, this is going to be the volume for the first one. This is going to be the volume for the second one. So this guy's going to be pH for the second one, pH for the first one. So we want to be really careful when they ask us these questions. You know, are they talking about the first equivalence point, or are they talking about the second equivalence point? Because it's going to matter. All right. If I go back to this one here with sulfuric acid, sometimes they'll say, give me an appropriate indicator for the complete neutralization of H2SO4. So if I wanted to see the complete neutralization, what they're referring to is I want to see step 2. If they're asking me for the incomplete neutralization of sulfuric acid, then they're saying, oh, I don't want to see so far as step 1, because now it's only halfway done. So be very careful as to what indicator you're picking, and be very careful as to say, you know, which one do you want, and therefore we have to look at the curve and determine the pH. Not only that, they could ask us and say, well, what's the volume of this? What's the volume of equivalence of the second, or what would be the volume of equivalence for the complete neutralization of H2SO4? And anytime they refer to the complete neutralization, it would be the second one, and anytime they refer to the incomplete, it would be the first one. There we go. All right, I'm going to stop there. Make sure now you check out with your online tutor, and if you have any questions with this, drop a line. Go double check some public exams. There's lots of questions there. See what types of questions they ask and how they ask it. And don't forget, we have public exam reviews done for you, questions in the learning content link under public reviews. And I'll see you guys again. Bye-bye.